Okay, welcome back to the second section of the chapter. We're going to move on. This second section is more to do with the processes involved and descriptions of what's going on, although it is all based on the maths. The maths of that very first section, using this binding energy graph to work out how much energy is released when it is unbinding or where it's actually binding together, is all really about practice. It's just getting that practice, so make sure you get plenty of practices in there, but again, this model is quite a nice model. So what we're going to talk about is really the processes, not the natural ones that happen as things fall down the sides, okay, so the natural decay process, but actually we're going to look at these ones that require a lot of energy. So moving down the hill from the left here in a very slow way potentially, and moving down rapidly. Now, just to break down this model, this model will have limitations. It's not all true. In real life, these are going to smash up the rocks when we're going down, but what we're actually doing in our maths is, if we're moving from our Fermi cliffs towards our iron lake, where we're actually going up the nucleon number, so we're increasing in size. So if we're thinking about our model, as our rocks fall, they're all sticky, they start sticking together, so perhaps a bit more like an avalanche falling from here, an avalanche of snow rather than a tumble of rocks. Down at the other end, a bit more usual, but again, you're not going to find big rocks splitting up. But in real life, yes, big nuclei can split up quite regularly. Some do it naturally, so right up at the extreme end here, over on the right, what you'll find is some nuclei will naturally fission, okay, split apart, and others need to be helped. So we're going to move into nuclear power, okay, and it's still the same natural processes, but when we're talking about getting humans getting energy from nuclei, we need to actually help it along, which costs a lot of money and a lot of research. But the basic process is that this splits into two halves. Both halves is about becoming more stable, it's about going down the hill, but the two steps are fission, where we chip apart the atom, fission chips, okay, work on that one. So chipping apart the atom falls down this end. If we in the process towards that central line, if we are going down this way, then this is fusion. Okay, again, just remind you, it's all about the nucleus, so it's nuclear fission and nuclear fusion. You can talk about atomic fission and fusion, but that's you know, like melting plastic. That's not the same. Okay. So all about this graph, and as I said, it's all divided on that 56 line. Okay, that most stable nucleon number. So all about moving in. So although we're going up the hill, it's still the same process. All right. So let's have a little look. But apologies, I've got it wrong there. Fusion at this end, and you can see the problems with similar words. Okay, so fission at this end. So nuclear fission chips might help him. And this is the phrase used by Rutherford when he first managed to split the atom, as they all say, but he actually said it's more like chipping a bit off. So, fission and fusion. What is it about? Well, obviously it brings in a lot of the stuff that you've done at GCSE as well, or should have done at GCSE, so nuclear power stations, chain reactions, things like that. So we'll do that more in the lessons, but in terms of filling the notes, we just need to have something very clear in our heads about it. But these are nuclear reactions. And that's not quite true. Some will naturally fission apart, but it's quite rare. Again, go back to the last chapter. It was a tiny bit right at the top of that graph where we had neutrons and protons So natural process, we had our betas down here. Oops, excuse me, terrible arrow. Beta plus and beta minus, moving them in. We had alpha was, you know, anything that was really massive, etc. We had other processes as well, neutrons and proton decay and so on, but we had a very small patch up here which was fission that was natural. Okay, but really small numbers, so we're not going to concern that. Most things are alpha and beta. So. Okay, so if we make them so they are happening, these processes are happening, then they are man-made. Okay, they are created in the vast majority of cases. They are not spontaneous. So let's be really clear. Radioactivity is that spontaneous, random process, okay, that we cannot control. Alpha, beta, gamma, all that stuff. However, I suppose, and random. We don't want that if we were talking about nuclear power. If we want to control it, we need to be able to control it. In which case, what we'll do is we'll need to actually do that in a much more rigorous fashion. So we need to be predictable, as it says there. So humans, nuclear power station already has, nuclear power rather has a bad enough press. We need to be able to control it very closely. So, fission, splitting into two smaller nuclei, and usually some shrapnel as well. So think of it as a bomb. Your bomb splits into half. You have two halves. You can't necessarily say how big the two halves are, but they're obviously going to be two roughly half sections of what you originally had. But where it splits, you're going to get some other particles come out as well. Usually neutrons, because the neutrons are no longer needed to bind them together. Remember, the bigger particles, the really big particles, needed a lot more neutrons than they did protons. But if we were to split from something up here to something about half the size, okay, so going from here to something about there, or rather two things, there we go, so the average is half the size, then obviously they need a lot less neutrons to proton ratio than they did at the beginning. Okay, so that's the finer detail, but basically that stability is the main idea from it. So for us, if we induce a reaction, man-made, okay, if we make it happen like we induce current, we can induce a reaction, then what we have is a slow moving neutron to actually cause the split. Okay, so back to my model of my bomb, it's actually not like a bomb. It's much more about a nucleus that's wobbling around. Okay, that's a bit big, let me get something smaller. So imagine my little Einstein is a nucleus and it's wobbling around. It's unstable, but it's not unstable enough to fall apart. But if I add a bit more mass, then what will happen is that extra bit of mass will just make it even more unstable, and because of this neutron to proton ratio then being wrong, it will be even further away from that central stable line, so that will cause that to then split apart. Okay, we have a nice animation, which obviously I'm not got at home, but we've got a nice animation that I'll show you in the lesson. So we have a slow moving, a low speed neutron. Oops, excuse me, can't spell neutron, which is what we call a thermal neutron. What do we mean by that? A thermal neutron is one that's moving around about the speed of things that are at room temperature. Yeah, so it's quite a low energy. This is not a high energy physics process. These are slow moving neutrons that are just moving around at around about 0.5 kilometre a second. Now that sounds fast, but we worked out that that's about the speed of particles like nitrogen, for example, in the air. Okay, they're not fast moving. Half a kilometre, kilometre a second. When we're talking about particles being released by nuclear radioactivity, we're talking near the speed of light. It's very, very different. Okay, so a thermal neutron, a low speed neutron, is absorbed by a nucleus. You strike it, you fire it at it, if it was that kind of rigorous, but it's a bit more random than that, unfortunately, because you just throw them in and see what happens. So it's absorbed by that nucleus, which increases instability. So that it splits. Into two. Okay, so it's always going to split into two because it's still tightly bound, but it's just, you know, you have that rupture. The process cannot be predictable as such, and we'll come back to this because it fits in with nuclear waste. We know that they are going to be things that are around about half the size. So in most power stations in Europe and UK and around the world, we'll use uranium-235. Uranium-235 splits quite predictably. Okay, so it's quite well controlled. Plutonium is used in some, so that's going to be 94, so it's 2 up, so it's a slightly bigger nucleus. Again, different isotopes, a bit less predictable. Or thorium, which is actually really predictable and has some other useful benefits. So most of that, say that article I gave you was about, to research was about thorium. Actually slightly potentially a better future than uranium, but we'll talk about the generic one, which is what most use, uranium-235. So we add a neutron, and that will split up into things like barium and krypton. Okay, plus a couple of neutrons. 2 or 3 neutrons will come out of this. Okay, so you put one in, causes it to fall apart, and 2 or 3 neutrons will come out depending on what these two rough halves are. As you can see, they are not halfway. Okay, but if we add them up, they'll still add up to near enough 235. Okay, these ones will, of course, quickly do the maths, will not add up to 235. That add up to less than 235. Okay, so 23. Oh, that doesn't work. 234. Let's make that one 89. There we go. I've never spotted that before. And if you add those up, that'll add up to 233, and therefore 2 lots of neutrons come out. Okay, so, oh dear, excuse me. So, don't take things off the internet without checking them. Okay, so yeah, splits into smaller. Some neutrons come out, and they come out with kinetic energy. Okay, so the energy released is worth putting in the kinetic energy, not just the neutrons, but of all of them. Now, worth pointing out at this stage, they're quite massive compared to those. Okay, so those are going to move quite slowly. Those are going to move a lot faster due to conservation of momentum. Okay, so they are no longer low speed, they're coming out at a really high speed. So we need, as part of the nuclear process, to control them, slow them down, so they can then carry on and do the next bit. Okay, so there's a little bit of cleverness goes on, and that's where we're going to come up with our next section, but for this moment we'll pick up on that. There we go, found the right page now. Okay, so the process that is often visualized at GCSE is that nuclear reaction we just had. So there's our uranium, we've added a neutron, instability, falls apart, 2 or 3 come out depending on the isotope of barium and krypton or other products, daughter products. Those neutrons then go on, and if they are slowed down in the process, then we can get them to be absorbed by uranium again, the next nuclei, and that can split again. For illustrative purposes, I have used exactly the same copy and paste. However, these could all be different products. Okay, so they will just split into basically two halves, and each of them then causes the next ones to split, etc. So if you have 3 neutrons come out, you could split 3 more nuclei. Okay, assuming they all hit. A lot of them don't. Okay, so it's a little bit more complicated than the ideal perfect GCSE version. So in terms of what's going on then, there are processes happening behind, but if we just talk about the general picture, then we can start to think about this idea of problems and so on. That's most of the descriptive stuff. So if we have something called critical mass, then we can have a reaction that is sustained. If I didn't have any more uranium nuclei, or not enough uranium nuclei, then you wouldn't get this growing effect. Okay, so this is like one match lighting another match, or set of matches, and the rapid increase, so positive feedback, exponential growth. Okay, if we can control it, then we can actually keep those in condition. Now, in terms of that, do we have enough to split? Be wary of that word, sorry. Again, we're not firing these in so that they split. We are hitting them, they are striking the atoms, and if they're the right speed, they'll be absorbed and they will fall apart. But we talk about splitting the atom, so just be really wary of that phrase, splitting atom. Okay, so as it says here, you've got to have at least a certain mass of uranium, of fuel, whatever that fuel is, to keep that process going. Okay, so if you have, excuse me, too many, let's start with too few. Uranium isotopes. I'm just being a little bit lazy there. So if you have too few uranium isotopes, then basically what you've got is not enough neutrons. Oops, excuse me. Striking uranium nuclei. Okay, process stops. The chain reaction cannot carry on. Okay, so this chain reaction, worth highlighting the word there. So that chain reaction is that whole chain of events happening. If you have too many isotopes of uranium, I should say, then what you get is a runaway effect, an uncontrolled chain reaction, which just grows in number and number in number. Basically, you have a nuclear bomb. Okay, so a nuclear bomb is where the energy being released, again, don't forget these are fast moving particles. That effectively means they are hot, they have that energy, so it's how we think of that energy. The kinetic energy of them, if they strike you, they're going to give you a lot of energy, they cause heating. If the number is increasing, then it gets hotter and hotter and hotter, and that's your nuclear bomb. If you have just the right amount in a power station, so at critical mass, then what you have is just enough uranium to keep it going. And what we mean by that is the number of neutrons given out, released in the process, so the number coming from our splitting atoms is going to equal number of neutrons absorbed. Or we shall stick with the process of striking, stroke splitting other isotopes. Okay, so at critical mass we have just enough mass to keep the process running without it running away out of control. So nuclear power stations are designed to have just enough mass to keep this chain reaction happening. If we're transporting uranium around, then again we use this whole, excuse me, I've just noticed a missing E. If we are transporting uranium fuel around, then as long as we have very small amounts of uranium, there's not enough to make that happen. So nuclear bombs need to be above a certain mass of unstable isotopes. Okay, if they're not going to cause a nuclear reaction. Dirty bombs and things like that, which terrorists are aiming to do, and this is why we are tightly controlled with our stuff, is our fuel, our sources, even though they're not unstable nuclei in this way, they're controlled by the Home Office, because if people put nuclear material, fissile material, fissile being splittable material, within a normal bomb, then it sprays that contamination around, it sprays that isotopes around, so things become radioactive. That's not the same as a nuclear bomb. A nuclear bomb is where the nuclear process releases a huge amount of energy. Okay, so a completely different thing. Right, so the other process, nuclear fusion, still happens with that chart. So again, down to our chart here, we've got a completely different process going on. So example is we are fusing together smaller nuclei to make a bigger nuclei, but we're still releasing neutrons. Okay, we still have that process going on. And when you get neutrons colliding, again, with enough energy, etc., then they become hydrogen isotopes. In this one we have hydrogen-2 and hydrogen-3 merging, so that's deuterium and tritium merging together. That's still going to release energy, because we'll find that the mass of our particles here are different from the mass of our particles here, and so we are changing the binding energy. Okay, so we're still giving out radiation. So in that process, what we have here is we've got low mass particles, I'll say isotopes, but I'll put in brackets because it can be isotopes or it could just be individual particles fusing together, but they're moving fast enough. Why do they need to be moving fast enough? Excuse me. So with enough energy, because you need energy to overcome the nuclear strong force. It's going to try and repel particles if you get them there. If they're positive, then again the particles are going to repel through the Coulomb force. So you've got forces trying to stop you merging them together. To get close enough, basically. For nuclear strong force to hold them together. There we go, that's a much broader, more helpful, I think, phrase to use, to hold them in the nucleus. Can't spell nuclei, excuse me, it is early in the morning here. Nucleus. And I'll just put in, you don't need this, but this Coulomb force. I'm going to change that to as Coulomb force prevents it. Sorry, that's a bit messy there. Okay. So, yeah, you need enough energy to make that happen. How much is enough energy? Well, we need to be moving fast enough with enough energy that's hot enough to make this happen. So the research on nuclear fusion is trying to recreate the conditions that's happening at the center of stars that are in their main stage. If they're in their main stage, or the bigger one dying, where you're getting nuclear fusion happening, they've got to be a high enough temperature. So this is about, give one of those numbers that is really useful, 8 million Kelvin. Okay, so when you can make gases, for example hydrogen gas, moving fast enough, you can get fusion to start to happen. Obviously this is pretty damn hot to be having on Earth, and this is where the nuclear fusion research is so expensive, because you need to have containers that don't melt when you're moving at these temperatures. So they're held within magnetic fields, they have that right hand force holding them going around basically in a donut torus fashion, or toroid as it's known, and that toroid is what causes them to then collide, etc., when they're going fast enough. But they are not actually sloshing around in a container, they're held away from the walls of the high temperature resistant metals in the hope that it doesn't melt everything. Okay, but really fast enough. If you make them fast enough, then you can get them to stick. That's the kind of key process of it. So where does that happen? Well, they've got to be small particles for that reason, that they have to move fast enough. You will not get, or it's really difficult to get large particles to move that quickly. But yeah, we get a lot of process around it. So just in terms of, excuse me, let's get rid of that. In terms of what that's going on, a little bit of extra detail. For most people, you could stop here if you want, that'll give you a lot of it. But again, let's link it back to that earlier thinking, because that will, you know, that will strengthen your answers and so on. Increasing the strong force. Okay, so if we were to fire at hydrogen ions, protons, okay, so let's just put that in, just remind you that's hydrogen plus. So if we were to take a hydrogen nucleus and start firing it around, then you need to overcome that. So again, let's just go with our idea of our spaced out nucleus here a little bit. You've got all those nucleus strong force holding them all together, etc. And I'm not going to get too messy and so on. But what happens is, if you add that proton to it, then what you're going to do, you're going to increase, just put in, adding proton increases the overall nuclear strong force. Obviously we're just talking about total because they're all individual forces, but the overall strong force between all the nuclei, sorry, nucleons, so each of the particles in the nuclei. Okay, and so because you're increasing it, that gives that explanation. I think this is much clearer to talk about than fission. Because of that, you need much more energy much more. It's a very steep cliff there, so much more energy to unbind them. Okay, so this probably is the easiest way to think about the nuclear strong force and why that it changes the energy. But yeah, stronger force being held much tighter together. To unbind them, you're going to need much more energy to make that happen. So binding energy is much bigger in this than it is in the other one, and that is why, if I get my graph back, this is why exam boards will use the graph this way up. Okay, because it's about this idea of how much energy is holding within it. Okay, so effectively this is stored energy rather than unbinding energy. Okay, and that extra bit, nuclei much more massive. As I say, opposite process going on. Beyond iron, we can see that the binding energy per nucleon, that graph, decreases. Okay, So what you'll find is that if we were to take, again, a bit of a rough idea of a sketch, if we were to take these, you know, it's a big, maybe not that big, a big nucleus, and we have our nucleons within it, and you've got your strong force and so on, but you know, the strong force between all of them, that's quite a big difference. So that's that distance x. If it gets to around about 3 femtometers, okay, i.e. the size of our nucleus, diameter of our nucleus is more than about 3 femtometers, then basically there's no nucleus strong force to hold it together, that is. Okay, so again, just that reminder, it all comes back to that graph. So where does it cross? What were the numbers? You know, 3 femtometers, you're getting onto round about here-ish. So x in femtometers. Force, nucleus strong force. Okay, so yeah, normally great, nice and stable where you can get things that are very small. If you're working on really small distances, then you know it's going to help you push apart. It's going to bind it more if you're in this area. So this is our binding energy kind of area. But again, a bit deeper work. But in terms of linking descriptions together, basically you've got a for this process here, I'll just put this out of the way, greater distances, let's say greater than 3 femtometers, 2 to 3 femtometers, there's a weaker resultant force. Okay, so you need to do less work. Needed, so that's work, force, distance, overcoming. Again, I don't like that phrase, but overcoming the binding energy, binding force. Okay, so yeah, it all kind of makes sense in terms of logic, but for most of this, it's not about those descriptions. It's actually thinking about the idea of what's going on. So previous 2 pages, that graph, using that graph, relating that graph to an equation like that one, bring in the previous page, or that one, you know, realizing it's all about energy released. Can you work out how much energy is released? Well, yes, you can, because again, you may, if need be, you'd be given this idea of the mass of each part afterwards. Okay, but again, just remind you, I'll find my data book as well. There we go. We know the mass of this because it's 235 lots of unified mass constant. So again, that mass number, as it's known in chemistry, you know, relative atomic mass, that for us it's the nucleon number, but the mass of each nucleon on average with its binding energy is this. Okay, so this is inclusive of binding energy. Okay, so just be wary, do not ever attempt to do the calculations if you are just splitting something like we are here in terms of, I have 92 protons, so I'm going to use that mass, and I've got the rest of them are going to be, you know, 140 whatever of those. Don't ever do that. Just use 235 lots of the unified mass constant. Okay, so calculations is what it's all about. The understanding about it's trying to make it more stable, and it's to do with a nuclear strong force is what you'll need for most kind of questions. Okay guys, next time we're going to look at the processes. We're going to go beyond that, so we're keeping that in the back of our mind, but it's all about, you know, the nuts and bolts of nuclear power stations and nuclear waste.